the fathers of the field, who is going to tell us about reflection positivity and its relationship to zeros.
Well, thanks very much. Thanks for the invitation. Thanks for the honor of being the first speaker. And I didn't say anything about relation. Compliment.
Okay, sorry. That's a relation.
Yes, a compliment is a relation. But this is going to be a mini course on reflection positivity. That's because I haven't done anything about polynomials for many years. So this is the closest I could get to the subject of the conference. And here I've listed a whole lot of people that over the years I've worked with on this subject, which developed, took time. A lot of people contributed ideas. So I want to make sure that you know I didn't do this all by myself. Of course you wouldn't, but just in case. So this is the, what shall I say, the political part, so to speak. Now the celebrated Liang circle theorem for the zeros of the ferromagnetic Ising model, which had a big impact in its day. I remember this very well. And it's very important generalization by Asano. I don't know how many of you have read Asano, but he was the one who really understood what was going on and was able thereby to generalize it to quantum mechanics, to the Heisenberg model and things like that, instead of the usual Ising model. How many people have read Asano? How many people have heard of Asano? Oh, great, okay. Unfortunately, he did not live very long, but he contributed a lot. But then there were many, many other people who contributed to this subject. You all know that. I won't list names. And it contributed a great deal to our understanding of phase transitions when it works, which it doesn't often, but when it does, it's very important. But this title of the paper in which this was announced by Li and Yang was called Statistical Theory of Phase Transitions. And the first remark is that it mostly led to a theory of the absence of phase transitions. Namely, if it works, it tells you that in this region over here in the complex plane, we're not going to have anything funny happen. So that's a theory of non-phase transitions. And if something does happen, well, it'll happen over here. So as I said here, its main use, mathematically at least, was to show that a certain region in the complex plane of parameter space was free of zeros of the partition function, and hence free of any singularity of its logarithm, or free energy. And by the way, I thought I'd put in a little commercial for myself and David Ruel, who just appeared. Namely, if you want to see what you can say about an antiferromagnet, I don't know if this is well known or not, but for an antiferromagnet, things are very different. They don't lie on the unit circle. And there's not much you can say, but what you can say is in this paper, if you want to take a look at it, it's kind of interesting because it uses the theory of several complex variables in a fundamental way. Okay. Now, one way to prove the existence of phase transitions is to prove that in one region of parameter space, no long-range order appears. Long-range order is the key word here. And in another region of parameter space, there is long-range order. So it either is or isn't. It's a two-valued statement. So somewhere in between, something funny must have happened. That means there's a phase transition. So if you can show this, that in one region there's no long-range order and in another region there is, you're in business. Now, it's usually quite easy to prove the absence of long-range order, say at high temperature, for example, if temperature is a parameter. And you do this by perturbation theory, cluster expansion, all kinds of ways to do it. There's a whole industry connected with that. But Usually it's just perturbation theory. So we have this region straightened out. Another example would be large magnetic fields or small magnetic fields. The hard part is to prove that long-range order exists when the parameter in question is sufficiently large. The parameter in this case would be 1 over the temperature, beta. One of the great historical mistakes of all times was to call, when it's cold, call this low temperature. It really should be called high something. And when it's hot, it's low something. That was a dramatic mistake. It's only fairly recently in the 19th century that sort of the common man understood that there was a continuum between cold and hot in weather. I used to think, well, there's cold and there's hot. The cold comes in the door, or the hot comes in, whatever. Anyway, now, one of the ways to prove the existence of long-range order is to use reflection positivity. Now, I'm going to assume this is going to be a very light talk, not many equations, in fact, no equations at all, so to speak, almost. And so this is a talk mainly for people who don't know what this is. And I will try to explain what it is and how it works. The details are for another day. And historically speaking, at least that I know of, it starts with Osterwalder and Schrader in 1973, who used this to prove something about quantum field theory. Now, I should tell you that there are several kinds of reflection positivity. And there are several ways in which it or that, it, them, they can be applied. And the one I want to talk about today is to prove a phase transition for a particular kind of dimer system. But that'll come at the end of the talk. So first I'm going to talk just about what it is, at least the kind that I'm talking about. Okay. Now, I'm going to begin with a fun topic that has nothing to do, much to do with statistical mechanics, although it's very important in some areas of the quantum many-body problem. And this is sort of bait for the analysts in the audience who like potential theory. If you don't like potential theory or you don't know anything about it, forget it. This is only 2 slides. So let me remind you about potential theory. You take the inverse of the Laplacian, which is a kernel, 1 over x minus y, in 3 dimensions at least. And so you apply this to a function on R3, and you integrate, and then you integrate it against another function. So this is a quadratic form. And this kernel is positive definite, which means that this quantity is always positive if f and g are the same function. Now, that's fine, but that's not what I'm talking about. I am not talking about this positivity. I'm going to talk about another positivity. Then the positivity that I want to talk about is the following. So we take a plane in R3, any plane you like is a plane, and you take a function, f, which is supported on the left half space. So here's a plane, f is supported over here, okay? And you take another function, which is supported on the right half. It's not the same function. They don't, but one is, they have supports on one or the other side of the plane. And I want to take f to be the guy on the left and g to be the one supported on the right. So this object here has no right to be positive. I mean, there's 2 different functions. One is supported here and one is supported there. However, it turns out, sorry, there is a positivity, nevertheless. And that positivity involves an inversion. So I can identify the left half with the right half just by the usual way. You just say if it's the z is the coordinate perpendicular to the plane, you just reflect through z. So we say that theta on a function on the right is a function on the left by inversion. And I can look at the energy when this guy is the reflection of that guy, and that is positive. Now, most potential theorists, as far as I know, don't know this fact. They know the first fact, but not this fact. It's not difficult to prove using Fourier transforms. So once again, if this is the reflection of that, it's positive. So that sets up a correspondence between left and right for any plane, anywhere. And this fact is called reflection positivity. It induces an inner product between the opposite sides of any plane. Any plane. You might call it the Narcissus effect. Why? Because this is closely related to the fact that when you look at yourself in the mirror, you appear to be on the other side of the plane, on the other side of the mirror, right? It is what Narcissus would have called reflection positivity if he had known about it. So now what good is this positivity? What's it good for? Suppose we want to maximize the energy. Now, it's the original energy. F is now any function. And there's some domain. And suppose this domain that we're interested in R3, there's the domain. Suppose it can be bisected by a plane, which is symmetric as far as the geometry is concerned. So, for example, think of a cube or whatever. Well, cube, and I guess that will do it. Then the function that, and you're trying to maximize some functional of the function f, which I don't write down explicitly, for example, some LP norm or whatever. And the thing that connects the function for different points is this Coulomb energy E. Now, you would like to know that if there's a maximizer for this problem that you're looking at, you'd like to know that the maximizer has the same symmetry as the problem. You see, not every symmetric problem ends up with a symmetric maximizer, as we all know. But on the other hand, using reflection positivity, which of course works, the LP norm condition that you put on is symmetric, but I take that for granted. Then by Cauchy-Schwarz, if I take any function and write it as a left piece and a right piece with respect to this plane, then I easily conclude that twice E of the F and its reflection, the left part and the right part squared, is less than the energy for the left part and the reflection of the left part plus the reflection of the right part and the right part. That's what I get out of anytime you have a quadratic with a positivity, you end up with a Schwarz inequality. Here it is. And so this tells you that one of these two choices is going to do better than that choice. At least one. Because this guy is less than the maximum of those two guys. Because the square is less than the product. Okay, so reflection positivity is a good way to tell us that the answer has to be symmetric. Now, this is of great use in statistical mechanics. Not the Coulomb problem in general, but in general, this kind of inequality is going to be very useful, as we will see. Okay. Is this clear to everybody that if you have a kind of positivity for a plane, then what you do on the left is what you want to do on the right. For maximum. And of course, if we're trying to do minimization, then if this gadget has a minus sign in front of it, then you do it the other way around. Now let's press our luck. Think of periodically stacked reflection planes in R3. So imagine some planes like this, kind of infinite sandwich, and equally spaced. And now we want to maximize now the total Coulomb energy. We can use this reflection trick. So you take one of the planes, you say, well, what I'm looking for will be symmetric with respect to reflection in that plane by the reflection positivity. Then, having got that, I now take the next plane and say, well, it has to be symmetric with respect to that as well, for the same reason. And then with respect to that guy as well, for the same reason. So I end up with a maximizer that is not only reflection positive with respect to one plane, but with all of them, so it's periodic. And if it also works in this direction, then I can end up with cubes. Now, I'm being very schematic about this. I mean, but you have to fill in the details by yourself. Okay. But this is an amazing fact. You can just apply reflections over and over and over again, and you end up with a periodic structure. Next. So, summary. So far, we've learned that there can be interactions with the property that they prefer to have states that are symmetric with respect to planes. Such interactions are called reflection positive. There are also systems that prefer anti-symmetry. For example, the Ising antiferromagnet. That would, like, if you reflect, you want to have the opposite of what you have down here, up here. So, and that's like a reflection positive, but with a minus sign. We still call it reflection positive. We can also call it reflection negative. Lots of words are used. So, for example, if you, instead of the Laplacian, is minus the Laplacian, is just the Laplacian inverse, but without the minus sign. So that would be reflection negative. Now, if this is still unclear, I will now discuss the Ising model, the ferromagnetic Ising model. So the energy, as everybody knows, is SI, Sj, nearest neighbors, on some lattice with a minus sign, which means that everybody wants to be parallel. And this Hamiltonian is, of course, reflection positive. That is, whatever you do on the left, however complicated you want to do on the right, here's a, whoops, I went in the wrong direction. Let me just temporarily go forward. So here's something on the right. It's just random. It is random. And here's something random on the left. There's some energy. I can lower the energy by taking either this and its reflection over here, whatever this may be, or the other way around. Reflect this over here. One or the other will have a lower energy than what stands here. Okay? And for the antiferromagnet, there's a minus sign, which means that whatever you do on the right, you want to do minus it on the left. You turn it over and put minus in, and that tells you that in this way you build up again reflections this way and reflections this way. You end up with a periodic structure, except the periodic means plus minus plus minus plus minus plus period 2 in the usual technical sense. Now, you might worry, here's the next slide, you might worry about the following fact, that I can do this only once. I cannot reflect here. Why? Because there's a boundary. I just have to take that into account. So what do? I really want to reflect here and use the argument again, but I can't. So what do? I wrap this on a torus. Well, in fact, first on a cylinder, if I'm interested this way, and then I wrap that onto this, so I get a torus. And for a very big system, you can easily prove that doesn't matter. So now I can reflect. The reflection cuts the cylinder into two pieces. So there are two cuts. There's one cut here and one cut there, if you really want to think about it. Okay. Now, well, so what? Anybody can see this. All we need is a bipartite graph. We're sort of proving the obvious. What good is it? Well, because now we can say something about correlations, which is not so obvious. Correlations is the new word. Because I want to prove that if the interaction is strong enough, then I'm going to get long-range order. This is quite a different story. So here's a partition function. The expectation value of any function is, of course, the sum over the spins times this function of the spins times the e to the minus the energy divided by the temperature. So for low temperature, that is when this 1 over T is big, we expect to get something interesting. And so we pick one of any plane you like, and we look at F, which lives on the left, and depends only on the spins on the left. And we can let G depend on the spins on the right. And we can define theta F to be the reflection of F, and so on and so on. And we get an inner product in this way, in the way I just explained. Just needed that positivity. That the energy is best when they're the same on left and right. That's the only thing I used. And it's positive, or in this case, the energy is negative because the partition function is, the exponential is positive. And this reflection positivity of functions now is a direct consequence of the reflection positivity of the Hamiltonian. So reflection positivity of the Hamiltonian gives, when you put it in the exponent and look at expectation values, it tells you something about functions. Now it's this point that gets very sticky if you try to do this in quantum mechanics. The reflection positivity of the Hamiltonian, you cannot split this exponential into two pieces in quantum mechanics, which is what I've sort of been doing without telling you. There are commutators to worry about and all kinds of complicated things, but you can do it, but it's not easy. So let's ask a specific question. Take a projector onto, for each vertex, we'll define the projector, which is +1 when the spin's at the vertex I, this psi I, and one of its nearest neighbors is our opposite. That's a bad case, and that is plus minus or minus plus, or 0 otherwise. And I is some collection of vertices, any collection you want, which I call capital I. And I take the product of those guys. Again, in quantum mechanics, we have to worry a little bit. And we want to find an upper bound on the expected value of this bad guy. So this says, what does this say? You're looking for the probability that all the vertices in this collection I that you've picked out are bad in a configuration. Okay? You'd like to estimate that. So here I have a bunch of vertices all over the place. And I want a universal bound on the probability that every one of them is bad. Okay? That starts to get interesting. And we want to show that for small enough t, that we can do this in a useful way, that it's unlikely to find mismatched spins on I. So we asked the question, which set I, which collection of I will maximize this? 1 over I, the volume of I, the number of points in I, times the logarithm of the expectation. Okay? So it could be 1 point, it could be no, well, it can't be none. Like 1 point, 2 points, 10 points, I don't know, maybe the whole thing. I'm looking at the expected value of the energy source. And well, maybe, wait a minute. No, sorry, I don't. I guess I don't want the log. And, well, I do want the log, sorry. I want the log because I want the nth root. That's why I want the log. And I would like this expectation to be something to the power n, where n is the volume of I. No matter where these vertices are in the world, whether they're next to each other. What's the worst case? So the probability of finding n mismatched edges anywhere anywhere, for any fixed number n, any n, is less than e to the minus n times a, where a is some positive number. Now I claim if we can prove that if the interaction Hamiltonian, or the temperature is small enough, then we can in fact find a positive a. That's universal. By reflecting over, and take your worst case and reflect it. All right. Let me repeat that. You want to know what happens if I tell you that n points, and n is anything you want, that there's a number a, so that if you pick any n points, 5 points or 10 points anywhere, there's a universal number so that the probability that they're bad is small. Small in the sense that it's less than something to the size of the set you're looking at. So the probability is bounded by, if this is, sorry, there should be an a here. So the probability that so it turns out that when the d is, oh no, so let me start at the beginning. I forgot, got myself lost. All right, now once you know that fact, that's universal thing. The Piles argument of 1936 tells you that you will have long-range order. That is, if this guy is mismatched over here, that guy arbitrarily far away is also mismatched with a probability greater than 1/2. Or if this guy is good, that guy will be good with a probability greater than 1/2. Let's put it that way. And how do you do that? Well, you say, if that's mismatched, and this one isn't, what's going to happen? In between, there has to be at least one curve, so to speak, running through this lattice, where on one side everybody has one sign, and on the other side of this curve everybody has the opposite sign. If they have opposite, maybe I should have said that, let's look rather at this guy being plus and this guy being minus. Let's look at it that way. Then there has to be a boundary where on one side of the boundary it's all plus and all side it's minus. Now, we know what that costs us. It costs us the size of the boundary. But how many boundaries can there be between 2 points arbitrarily far away? Well, you can estimate that. That's very simple geometry, how many boundaries there can be. So you have a competition between e to some number times the n, where n is the size of the boundary, minus this a. I should have put an a in there. A is now 1/t, I guess. And I can easily make that smaller than 1/3 by letting t be large enough. So that's the argument of Piles. Now, Piles had this argument in 1936, but he made a mistake. The mistake was he was not able really rigorously to prove what I just said, that there's a universal number so that the probability is just that universal number times the size of the boundary. It's a rather delicate argument if you have to do it from scratch. And but that was done by Russian later, and as far as I remember. And so that by the time reflection positivity came along, it was well understood. But the point is that this result, which you get by reflecting over and over again, maybe I should have said that more explicitly. If I have a mismatch somewhere, then the probability of getting a mismatch next to it, the vertex next to it, is a little bit bigger than 1/2 because of the interaction and the reflection positivity. So I keep reflecting. And the worst case turns out to be, just by reflecting, that the worst case is when every vertex is mismatched. Every vertex. And then it's easy to calculate. If every vertex is mismatched, that means I've taken the ferromagnet and made an antiferromagnet out of it. Okay, now, let's talk about dimers. This is what I put in the abstract, so I may as well talk about it. Well, everybody here, I think, knows what dimers are. You take a lattice, you put dimers matchings. But we're not talking about perfect matchings now. We're talking about monomer-dimer systems. So we have dimers, and we have empty sites where nothing is. But you cannot put two dimers on the same site. Everybody knows that. We also know, by looking at zeros of the polynomial generated by the dimer fugacity, this polynomial has zeros on the imaginary axis. So when there are monomers around, nothing can happen. And the only time anything interesting can happen if you have dimers is when you have pure dimer coverings. Then something can happen. But otherwise, the zeros prevent anything happening when you have monomers as well. Okay. Nevertheless, I'd like to get something happening. So we're going to invent a model with interaction. So once again, I'm just repeating myself now. If you just have dimers, you can have phase transitions as you vary the edge weights of the dimers, but otherwise nothing can happen in terms of phase transitions. Okay, that was 1971. So in order to, or in an effort to get something interesting for the monomer-dimer system, we think of the dimers as diatomic molecules. And we introduce an attractive interaction between neighboring dimers. So make it look a little bit like an Ising model. This was proposed by Heilman and myself in 1979. And we gave examples in 2D and in 3D as well of these kinds of interactions that would induce a phase transition, and more precisely give you long-range order and therefore induce a phase transition, as I explained before. But for purposes now, let me just do the 2D example. And that goes as follows. Now, now you remember that, just to remind you, Castellane and Temperley and Fisher computed the partition function for the pure dimer covering. And you can do it in several ways, including doing it by the transfer matrix method. But they didn't do it that way. So now we're going to talk about a non-zero density of monomers, which is not covered by the Castellane-Temperley Fisher method. Or the transfer matrix method. Now, so we're going to introduce an interaction that gives us a negative energy, which is good, when two dimers are oriented like this. So here's one dimer, here's another dimer. When they're like this, next to, or like that, they have an energy. They like to be this way. Negative energy. Okay, and I'll show you a picture of that in just a second, make it clearer. So these molecules attract each other. But, so they do, although they attract each other, it's not clear whether this attraction continues or gets dissipated. That is, whether you're going to, with low enough temperature, that is strong enough interaction, nearest neighbors will tend to be aligned the same way. That much is clear, but does that alignment continue forever and ever and ever? Or does it just sort of break up after a while? And so it turns out that reflection positivity tells us that e to the minus ht, which is e to the minus j times the number of edges that are correctly oriented, number of things like this or like that, that this thing has reflection positivity and therefore eventually long-range order. Now, let me see. Here's a picture. So this was made by Ian Yauslin, my co-worker on this. Here's what his picture of a liquid crystal looks like. I mean, the liquid crystals, by the way, that's what you see on your television screen at home. There are long molecules, which just like to line up in the same direction. But they can just line up this way or that way or any way. And here is the thing on a square lattice. So anytime two guys are next to each other and are next to each other and in the same orientation, you get some negative energy. So these red wiggles are the negative energies I get. So to go back again, that the weight is e to the minus some constant times the number of edges with correctly oriented dimers on both vertices. There's two vertices, dimer this way and a dimer that way. That's the partition function, or the Boltzmann factor. And what we're hoping for, what's the reason for this? We're hoping for the following, that we will be able to prove, using reflection positivity or any other means, that if the temperature is low enough, that is, if the interaction is strong enough, if I condition on some dimer being somewhere, for example, this one being like that, and I look infinitely far away, I look on the moon, that I will see dimers oriented in the same direction. What I would like not to see, if I have, I'm trying to model liquid crystal, I would not like to see translational order. You see, the dimer, if I take a vertex over there, and there's a probability that if it's hanging, a dimer is hanging from it, that there will be another one, that this dimer will be in the same orientation as the one I fix condition on over there, but it could be in two places. It could be either here or here. In other words, I don't want to see any lattice structure. I don't want to see any translational order. I want to see orientational order, but not translational order. I don't want the dimers to line up like a checkerboard. That's the characteristic of a liquid crystal. And that's the reason for this model.
Sorry, why do you say you don't want to have that happen?
Sorry, who's speaking? Oh.
Why do you say you don't want that to happen?
Because I want to model a liquid crystal. And the liquid crystal, which I just showed you a picture of, has the property that it's a liquid. There's no translation. It's really a liquid. You can, well, you can squeeze your touch screen. You can, well, at least some of them, you can press and you see that it's a liquid behind it. But the molecules are lined up. But there's no translational order as in a solid. There's only orientational order of the molecules. That's what I would like to see. I'm trying to model it. Up to this point, there had been no model of any kind with this phenomenon where you had the potentiality for two kinds of long-range order, but only one of them appears. Okay. So, by the way, how am I doing with the time?
But another 5-10 minutes.
Okay, good. Thank you so much. Okay. So we expect the following. What do we expect? We expect that if the interaction strength divided by the temperature, which is what counts, is small, smallish, that will not be any kind of long-range order of any kind. It'll just be a jumble. If I condition on a dimer being over here, what goes on the moon, it's just independent, it's just random. That's what I expect at when J/T is small. Okay, that's easy to prove. Again, you do some perturbation theory, whatever. That's not difficult. Now, we expect that above a certain critical value of J/T, there will be orientational long-range order. So that means if J/T is big, that if I fix this guy as oriented this way, vertically, then I look at the moon and I look at a dimer on this huge thing, there will be more than 50% chance of the dimer over there, that vertex being this way or this way, but not that way. That's what I, now, and, okay. Yeah, so that's the crystallization part. So if you shine light on it, on this thing, which is what you do with televisions, or electric fields or whatever, you'll see things. It'll be visible that there's some order, as you would get in a reflection from a crystal, because the dimers are oriented in the same direction, not perfectly, of course. But what we would like to see is that for suitable values of J/T, there will not be translational order. That's what we'd like to have. So this is hard. Now this is the liquid aspect of things. That's why it's called a liquid crystal. Now since that time, when this was introduced, other models have appeared, and I'm not going to tell you about them because that's not the purpose of this talk. But what was done was in 1979, Heilman and I proved that you did have this long-range orientational order. And again, we used reflection positivity. It's obvious that if you draw a plane through the bonds of this Z2, you draw a plane, a line, I should say, that the interaction is such that whatever you do on the left, you want to do on the right. So if I tell you what's on the left and what's on the right, then either left and its reflection or right and its reflection will have a greater probability than the original thing you gave me. That's obvious from the interaction. It likes if it's like this, you want to have that. If it's like this, you want to have that, and so on. That's clear. But that's not quite enough because of the funny nature of this thing, that what's going on is not just one point interacting with another point. As for the Ising model, it's much more complicated. It's a whole dimer interacting with another dimer. So to do the reflection positivity game, you have to take as the basic unit not a vertex, but a whole square of vertices, and play with that as the unit, as it were. So it gets to be a lot more complicated. But it's the same argument. Reflection positivity tells you that eventually the left and the right want to be the same, and this sameness propagates out to infinity if the temperature is low enough. And we did this in 1979. And then we conjectured that there would not be any translational order. So this guy out there is like that, but it could as well be this way. And that took 38 years. A lot of people tried to prove that, or at least some people tried. And this was done by Ian Yauslin and myself in 2017. And a couple of years ago. We did not use for this any reflection positivity. We did not use any Piles argument. The Piles argument was used in part B, as I explained before, but here none of this worked. What did work was a Pirogov-Sinai argument, and I understand somebody's going to talk about Pirogov-Sinai in this conference. That's very nice. So that did work, but it's very, and if anybody can find a really neat proof of this that's simpler, go ahead, because it's very complicated. It's because there are all kinds of possibilities of the way these guys link together. I mean, it's after all a two-dimensional object now. It's not a it's one-dimensional, not a zero-dimensional object. Okay, so you can look it up in the archive. So let me summarize what I did, or what I tried to explain. So I tried to explain what reflection positivity is, what it's good for, and it's the property of an interacting system in which there is an involution of some kind. Not necessarily pure geometric reflection. For example, you remember at the beginning I talked about the reflection positivity of the Coulomb potential. Remember? Now whatever charge you put over here, you want to put the same one over there. Well, there's another involution you can have with respect to the Coulomb potential. It's conformal invariant. So another kind of involution you can have is inversion in a sphere. This was understood by the ancients, right? That Coulomb forces work very nicely under inversion. Take a sphere, you can invert the outside to the inside. So it turns out that you can have reflection positivity for inversion in the spheres for the Coulomb potential. This was done by Rupert Frank and myself. So just some kind of involution, and usually associated with reflections in a plane, so that the interaction energy is lowered or sometimes raised when the right side is reflected in the left or vice versa. After making a choice and applying this repeatedly to many parallel planes, one can prove that the energy minimizer has a periodic structure. That's the lesson. When a probability measure has this property, it follows that expectations satisfy the same property, and this part is very difficult in quantum mechanics. This thing I just mentioned, it can be done in many cases, but it's much harder than in the classical case because of commutators. And so this leads not only to periodic structures, but also, very important, to an estimate that the expected value of the number of bad boxes or whatever is less than e to the minus some positive constant times the number of boxes, regardless of where they are, which is quite striking. Because you might think that if you nicely sort of combine things in a nice, smooth, geometric way, maybe it can become not so improbable. But no, it's not true. There's a bound for any number of boxes anywhere. And so when the effective interaction becomes large, when the parameter, say temperature, for example, is small, and then you apply a Piles argument, and this leads to a proof of a phase transition. And with that, I say thank you for listening.
Any questions?
So it kind of reminds that, what is that called, Steiner symmetrization when you
Yes.
prove in the parametric results.
Yes.
But so this was first approach to prove that certain is
Yeah, but it's no. Yeah, I've tried. As a matter of fact, it's a very good point that you make. In principle, it ought to be the case that reflection positivity would give you the isoparametric inequality, just keep reflecting and reflecting, but I could never quite make this work. There are technical problems, but you have a good idea here.
Yeah, but the thing is that, but Minkowski's approach was different. So Minkowski was log concavity, so he replaced kind of.
Yeah, but okay,
so
but
maybe here also instead of.
Right, maybe you're right.
Yeah.
Go ahead. I mean, it's a very good intuition.
Maybe this is the way to replace in the great physics equations that method of reflection positivity by some kind of log concavity, because that's what Minkowski did.
Yeah, but you don't need log concavity, of course. So here's an object. Okay, let me do the following. Take a plane, cut it into two equal areas, which I can do. Right? Okay. And then I easily see that I can take the left and reflect it over here and put the two together. That's a legitimate thing to do. That matches nicely. Or the other way around. One of the two choices, left, or right, will have a perimeter that is at least as small as the one you started with. Now you do it with a different direction, and a different direction, and a different, keep doing this. All the time splitting the thing so that you have equal areas on both sides. And then reflect. Over and over and over again, what will you end up with? Well, unfortunately, you can end up with a disaster. You can separate after a while.
But this is why Steiner had slightly trickier symmetrization.
Yeah, okay, so, but all right, let's go on. Any more questions?
Can you say anything more about the case in the non-commutative case, or what is involved in showing leading to the long-range solutions when you're talking about quantum mechanics?
Well, no, I cannot in a few words, but it's I mean, the typical situation is you whatever you're dealing with, you have to take some plane. So there's the energy of the left side, the energy of the right side, which is well defined, you know what that. And then there's the interaction between the two, some kind of interaction, which involves quantum mechanical operators. And you would like very much to split this, write this as the product of three exponentials, which of course would not necessarily be self-adjoint anymore. And obviously, so now you're not sure what you've got at all. In any case, it's not right. And I mean, the trace of, we don't have a nice inequality for well, we do have one actually, but it's not good enough for the trace of the product of three operators. And but in any case, you can't split it this way. It's because of all the commutators that are hanging around when you try to do that. And so what you have to do is you write e to the exponential of this sum of these three operators, the left, the right, the middle. You write that as a repeated, use the Trotter product formula. So if I call this L, middle, and right, I write as e to the L over n, n is some big number, e to the middle, e to the right, and repeat, repeat, repeat. And then try to split that up. That you can do. You can split these separate traces, because they're already in this form. But then you don't know what you've got anymore, because you don't have what you think you have, which is a copy of the original problem. Because the original problem, when you've done this, is not just the original product. So it takes work. But this was first done for the Heisenberg model, at least by Dyson, myself, and Barry Simon. After modeling us on Froelich and Spencer, and Simon, who showed the long-range order for the classical Heisenberg rotor. But this was very hard, very hard. So that's all I can tell you now. You can imagine, you just can't do all the things you think you can do. It's so nice if you're in this classical world where, A times B is the same thing as B times A, and it just doesn't work that way.
We have one more quick question.
Yeah.
Is it obvious that you cannot reach this liquid crystal state by changing from lattice to something a little bit disordered?
I'm saying
We're discussing lattice, right?
Yes, right.
So now suppose I'm allowed to introduce structural disorder.
Oh.
And no interaction between dimers. So can I still get liquid state? I mean, liquid.
Physically, yes, but mathematically it doesn't work. No, here, this reflection positivity method, unfortunately, really depends on having strict geometric. You can't change the rules. I mean, it's very inflexible that way.
But you were not using reflection, right, in your proofs?
You know, we did.
Oh, you did.
We did. You mean the proof of that it's of the crystallization with Heilmann? Yes, we did. That's why I said you accept that maybe what I confused it was that you cannot just simply reflect sort of vertices to vertices, because what's involved are dimers. I mean, you're not allowed to split a dimer in half, right? You can't do that. So you have, if you're going to reflect, you have to take as a unit, not a point, but 4 points. And all the things that can happen on those 4 points, which are a lot. You can have this, you can have this, you can have this, you can have that, and so on. And that's going to be your unit. So the Hilbert space, thinking quantum mechanically, the Hilbert space at a given point is not just C2 anymore, it's some very high dimensional thing. And so that takes a little work. And then you have to follow this with a Piles argument, but it does work. Am I being clear? Yeah, okay.
Okay, let's take a 4-minute break and...
Oh, I'm sorry I went over.
No, you didn't, absolutely not.
Okay. Thank you.